How many people say yes? People say no. Okay, yes, okay. Good intuition. So in fact, that's our a theorem. So if f is monotonically, let's say, increasing, the proof for decreasing is similar on, let's say, an interval AB, then I claim that this actually means that f of x plus and f of x minus exist at every point for all x in the NAB. Let's see if we believe that. Why do we think that's true? What's an argument? Yes. Yep. As x approaches from the right. Yeah, pluses for me from the right and minuses from the left. Okay. Now you have me wondering whether I agree with what's in the book, but let's take this to be plus from the right and x minus from the left, because that's sort of what the notation indicates. Okay. Okay, what's the idea here? Why do these things have to exist? Yes. Yeah, the same ideas should work for decreasing as well. We're just going to take one case here. Why is this true? It feels right. Why is this true? Well, I claim the following. I claim, in fact, something more is true. Would you agree that, maybe this should help us see why this is true, that whatever the value of x is, it has to live between would you agree that whatever this value is, it has to live between the value of anything on the left and the value of anything on the right? Yes? Okay, by monotonicity. So if I look at all the values it achieves on the left and take their supremum, it should still be at least as big as that, right? And if I take all the function values on the right and look at their infimum, then the values, this point should be less than or equal to that infimum. So certainly this is true of ft, where, here I'll just write like this, where t is on the right, t is in xb, and this will be the supremum of t, where t is in ax. So that should be clearly true, right? Okay, so of course I've just said sup and inf here, but how do we know the supremum exists? Help? It's bounded. These values are bounded by f of x, right? So we're okay that this exists because it's bounded. Okay, bounded above and bounded below, similarly here. Okay, so there was no problem in saying that. Okay, so does that help us? Does that give us some idea of what's happening? Let's see. So, what's the idea? Let me redraw this picture here. Suppose I have a monotonic function, and let's take a point x. And in fact, if you don't mind, I'm going to call this supremum If you don't mind, I'll call the supremum A. Let's call it A, which is the supremum of all the values on the left. Okay. And now I claim A is going to be that A, in fact, is going to equal what? What do you think I'm going to claim? Yeah, I'll claim that it's f of x minus. Okay. So let's see here. Let's draw ourselves a picture. Here is x. Here is, maybe it's doing something like so. Here is f of x. But the supremum of all the values on the left is going to be this number A. Okay. And so all I have to do to verify that it's in fact f of x minus is to show you that the limit of all the values coming from the left is in fact this number A. Well, let's take an epsilon ball around A. You give me an epsilon ball around A. Doesn't matter whether it contains the other side or not, but if I look at A minus epsilon, well, then we'll just make an argument there. So given epsilon bigger than 0, consider A minus epsilon. Well, if I look at this number A minus epsilon, certainly there's some values that of f of t that are bigger than this because it's a supremum. So there exists a delta such that f of x minus delta is bigger than A minus epsilon and less than or equal to A by the definition of supremum, since A is a sup. Okay. Okay. Now that means that there's at least one point that I can find to the left whose value lives in here. Can I show that all the points within some neighborhood on the left must live in this epsilon ball? Yes, because the function is monotonic. So all the points in here have to be where? In between. So in fact, this delta works. So, but then any t in x minus delta x must satisfy f of x minus delta is less than f of t is less than or equal to a. So f of t is in the delta ball, is in a minus epsilon a, as desired. Okay, so that's the basic idea. The argument's similar for the other side. Okay. So what have we shown? We've shown this claim. Similar argument on the other side. Okay, so the corollary to this fact that the f sub x plus and f sub x minus exist is, in fact, that monotonic functions have no discontinuities of the second kind. Oh, really? Okay, that's interesting. All right. Okay, well, let's see. This actually has a very interesting consequence, and that's the following theorem.